Hey guys, today we're going to look at interpretations and applications of the derivative and the definite integral. Now we're going to do both here because most FRQs are not solely just based on derivatives or solely based on integrals, but actually a combination of both. And we need to be able to understand how both come into play into these FRQs. So just as a reminder here, when you are finding the derivative of a function, the function typically represents the amount of something. So when you get the derivative, the derivative of an amount is equal to the rate at which that amount is changing. However, when you're integrating a function, typically that function represents a rate. And so when you integrate, what that value represents is the amount of change over the indicated interval of time, which is the a to b as shown on the integral. So let's look at this scenario to see how we can interpret those answers. It says here, water is currently being drained from a swimming pool. R of t represents the amount of water measured in cubic feet that is in the swimming pool at any given time measured in hours. What would R prime represent and what would the units be? So R of t, first of all, represents the amount of water. So if we find the derivative, remember the derivative of an amount represents the rate at which that amount is changing. Now, since this represents the amount of water, then this means that the derivative would be the rate at which the amount of water is changing. Now, when you find the derivative, remember that this is a rate. So the units here would be, we have cubic feet and hours, so it would be cubic feet per hour. Now, for this next question, it said, what would the integral from a to b of r prime of t equal r of b minus r of b represent? And what would the units be? Now remember, here we are integrating the derivative of r of t. And when we find that answer, that is equal to r of b minus r of a. So what you're getting here is the amount of change in the water level. From t is equal to a to t is equal to b. Now your units, since this represents just an amount, then it's not over hours. This would just be cubic feet, because that's the amount of the change in water level. Now let's start applying this to actual partial FRQs. It says here that the table below represents the velocity in feet per minute of a particle at given values of time in minutes. Approximate the value of the integral from 0 to 30 of v of t dt using a midpoint Riemann sum. Using correct units of measure, explain what this value represents. So if we're going to use a midpoint Riemann sum, that means that each interval has to have something in between. So I would go here from 0 to 10, 10 to 20, and 20 to 30. So that way I can use the midpoints, which are located at 5, 15, and 25. So here we go. If we want to get this approximation, that's the integral from 0 to 30 of v of t dt is approximately, now if you look at each one of these rectangles, they all have a base of 10, since it goes from 0 to 10, and then 10 to 20, and then 20 to 30. So we can put 10 on the outside, and then for our function values, we're going to use the midpoint. So f of 5 plus f of 15 plus f of 25. And now we're going to plug in those values. So we have 10 times f of 5, which is 1.6, plus f of 15, which is 3.1, plus f of 25, which is 1.6. If you add all of this together, 1.6 plus 3.1 is 4.7, plus 1.6 would give us 6.3. So 10 times 6.3 is going to equal to 63. And this is in the units of just feet. Since we integrated, remember that this is an amount. So what does this mean? Now we know when we integrate velocity, what that gives us is the distance, which distance by definition is the change in position. So what we could write here would be the particle, and this is what that value represents, change 63 feet in position over the first 30 minutes since we integrated from 0 to 30. So when we're writing our representation of the values, you want to make sure that you mention everything. Not only did I mention the 63 feet, but I also mentioned within the time that was given, which was the 0 to 30. Now we're going to find the exact value of the integral of 5 to 25 of a of t dt, and using correct units, explain what this value represents. Now, when we integrate acceleration, what that gives us is velocity, which is exactly what I have here in my chart. So here I can apply the FTC. So the integral of 5 to 25 of a of t dt is going to equal to v of t evaluated from 5 to 25, which is equal to v of 25 minus v of 5. We can plug in those values. V of 25 is 1.6 minus v of 5, which is 1.6, and you end up with 0. Now since we integrated and we got velocity, this is 0 feet per minute. And now what does this value represent? In this case, since this represents the change in velocity from t is equal to 5 to t is equal to 25, in this case, velocity went back to its initial velocity. So there is no overall change since we end up with 0. So we can state here that the particle has no overall change in velocity from t is equal to 5 to t is equal to 25 minutes. Now let's look at a couple of calculator examples. Here it says that the temperature of water in a tub at select times is modeled by a strictly increasing twice differentiable function w, where w of t is measured in degrees Fahrenheit and t is measured in minutes. Now just so you know, when you see this twice differentiable, that means that we can take w and find its derivative twice. That's all that means. Okay, and now we also see that it is strictly increasing. So maybe that's something that we'll need, I don't know, but just in case. So first part here, it says to estimate the value of w prime of 12. Using correct units, interpret the meaning of this value in the context of the problem. So the chart that we're given is w of t, and if we're trying to estimate w prime of 12, that means that we have to find the slope of the secant line. So 12, t is equal to 12 is between 9 and 15. So if you want to find this estimate, we would have to do w of 9 minus w of 15 over 9 minus 15. W of 9 is 61.8 minus w of 15 is 67.9 divided by 9 minus 15, which is negative 6. Now I'm going to go to the calculator here so I can get this actual value, since this is a calculator question. We have 61.8 minus 67.9, and then we're going to divide that by negative 6, which gives us 1.0166. Now our units here, this is a derivative, so this would be degrees Fahrenheit per minute. Now what does this mean? When we write the interpretation, especially for derivatives, we want to indicate the behavior of the function based on that derivative. So what we can say here is, since w prime of 12 is greater than 0, the temperature is increasing at a rate of 1.0166 degrees Fahrenheit per minute when t is equal to 12 minutes. Now here we have evaluate for the integral from 0 to 20 of w prime of t dt. Using correct units, interpret the meaning of this value in the context of the problem. So since we're integrating w prime, that means our answer would be w of t, which are the values given here in the chart. So here I'm going to have to use the FTC. So the integral of 0 to 20 of w prime of t dt is going to equal to w of t evaluated for from 0 to 20, which is equal to w of 20 minus w of 0. Now w of 20 is 71, minus w of 0, which is 55. And 71 minus 55 is 16. Our units here, since this is in degrees Fahrenheit per minute, and remember what we got here is w of t, then this is just 16 degrees Fahrenheit. Now what does this value mean? This means that the temperature changed, a total of 16 degrees Fahrenheit during the first 20 minutes. Since our integral is from 0 to 20, that's the first 20 minutes. Now for this next part. For the interval of 20, for t is between 20 and 25, the function w that models the water temperature has its first derivative given by the function w prime of t is equal to 0.4 the square root of t times the cosine of 0.06t. Based on this model, what is the temperature of the water at time t is equal to 25? So what we're looking for here is w of 25. Now we're given w prime. So if we need to find the actual function value, that means that we would have to integrate. Now in this particular case, they do give you an interval. So what we can do here is write an integral from 20 to 25 of w prime of t, which is 0.4 square root of t times the cosine of 0.06t dt. And that's going to equal to w of 25 minus w of 20, which the good thing here is that we are given w of 20 in our chart. So once we get this value using the calculator, we make it equal to w of 25 minus w of 20, which is 71. So I'm going to go to my calculator now, and I'm going to type in my function. So 0.4 square root of x. I move to the side here to make sure that cosine is not inside of the square root. So times the cosine of 0.06x. Enter. I'm going to also adjust my window. Since we're evaluating from 20 to 25, I'm going to adjust my window so my x's are also 20 to 25. And now let's graph it. Now again, it doesn't really matter so much what my graph here looks like because the calculator is going to get the value that I need anyway. So now I'm going to go to my second calc menu and integrate. My lower limit is 20 and my upper limit is 25. and I get a value of 2.0431. So 2.0431 is going to equal to W of 25 minus 71. So to solve for W of 25, we would just add the 71. So W of 25 is going to equal to 73.0431 degrees Fahrenheit. Always remember to include your units. And that would be my final answer. Let's look at another calculator question. We have here that a pan of biscuits is removed from an oven at which point in time t is equal to 0 minutes. The temperature of the biscuits is 100 degrees Celsius. The rate at which the temperature of the biscuits is changing is modeled by the function b prime of t is equal to negative 13.84 e raised to the negative 0.173 t. Find the value of b prime of 3. Using correct units, explain the meaning of this value in the context of the problem. Since the function that we're given is the derivative, then all we have to do here is plug in 3 into that function. So again here, I'm going to go to my calculator. I'm going to clear this out. I'm going to type in my new function, which is negative 13.84 e raised to the negative 0.173 x. Enter. Now I'm going to adjust my window because remember that this is my window from before. So I'm just going to change this to 0. Let's go to 10. Now you can see that the graph, right, is increasing. So that means that its temperature is going to be, that the graph is negative, right, because this is the derivative. So that means that the temperature of the biscuits is going to be decreasing. So let's go ahead and get the actual value that we're looking for. We need the derivative, so I'm going to go to option 6. Oh, no, we don't. This is the derivative. Just kidding. We need the value at x is equal to 3. And that gives us negative 8.2363. So negative 8.2363. And then our units here would be degrees Celsius per minute. Now, what does this value represent? Remember, this is a derivative, so we have to make sure that we indicate what this means in terms of the behavior of the actual function. So we can write here, since b prime of 3 is less than 0, the temperature of the biscuits is decreasing at a rate of 8.2363 degrees Celsius per minute at t is equal to 3 minutes. So notice that I didn't write negative 8.2363, and that's because I already said that it was decreasing. So just a side note there. For part B, it says, sketch the graph of b prime of t on the axis provided. Explain why the graph makes sense in the context of the problem. Now remember, the calculator already did that for us, and it looks like it's increasing, but it's kind of leveling out. And if we kind of increase this window, the x max, let's just say to 20, you see here that it's trying to reach the x-axis, but it doesn't really reach the x-axis. Let me increase that window again just so you can see that. Let's do 30. You see how it's never above the x-axis. And the reason why I'm pointing that out is because that's going to make sense. And I'll explain why. So our graph looks somewhat like this. Now, why does this make sense? B prime of t represents the rate at which the temperature of the biscuits is changing. And this is after it is removed from the oven. Now, it makes sense because I'm going to finish off this explanation and then I'll give you more of a rundown. So the graph of b prime of t is less than 0, indicating that the temperature of the biscuits is always decreasing. And this makes sense because if the biscuits are out of the oven, the temperature can't increase on its own. Think about it, right? If you take biscuits out of the oven, those biscuits are at its hottest temperature the moment that it comes out. Then it's just going to gradually decrease in temperature and get cooler. It's never going to get hotter again unless you put it back in the oven. So that's why this graph makes sense. It's never going to cross over the x-axis and become positive, because then that would indicate that the biscuits would increase in temperature. But a biscuit cannot just get hot on its own. Okay, moving on to part C, it says at time t is equal to 10, what is the temperature of the biscuits? And show your work. So we have to come back here into the problem and see what other information is given. We are told that at time t is equal to 0, the temperature of the biscuits is 100. So that means that b of 0 is equal to 100. So if I have one function value and I'm looking for the other, right, this helps me determine what the intervals of my integral will be. Since here I'm looking for the temperature of the biscuits and the equation that's given is the derivative, I want to find the antiderivative. So I would set up an integral from 0 to 10 of b prime of t dt, because that will equal to b of t evaluated from 0 to 10, which is equal to b of 10 minus b of 0. So I can get this value from my calculator, because again, the calculator can find the derivative on its own. The integral. So I'm going to go to second calc. I'm going to go to option 7. My lower limit is 0. My upper limit is 10. And I get the value negative 65.8172. So negative 65.8172 is going to equal to b of 10 minus b of 0, which is 100. So to get b of 10, we would just add the 100 over. Therefore, b of 10 is going to equal to 34.1828 degrees Celsius. Let's continue practicing. A cylindrical can of radius 10 millimeters is used to measure rainfall in Stormville. During the first 5 days of a 60-day period, 3 millimeters of rainfall had been collected. The height of water in the can is modeled by the function s, where s of t is measured in millimeters and t is measured in days for 5 to 60 days. The rate at which the height of the water is rising is given by the function s prime of t is equal to 2 sine of 0.03t plus 1.5. Find the value of the integral from 10 to 15 of s prime of t dt. Using correct units, explain the meaning of this value in the context of the problem. So here again is another calculator question, so the calculator can do this work for us. So we're going to integrate from 10 to 15 of s prime of t dt. So I'm going to go to my calculator. I'm going to go to my y equals menu, and I'm going to type in my new function, which is 2 sine of 0.03x plus 1.5. I'm going to also adjust my window here because this is for the interval from 5 to 60 days. So I'm going to go from 5 to 60. And now we'll graph that. So now we're going to integrate. So we go to second calc. We go to option 7. Our lower limit is 10. Our upper limit, oh, oops, I pressed something. Sorry, second calc, 7. Lower limit is 10. Upper limit is 15. And we get this value of 11.1592. And since we just integrated a rate, this represents the amount, and this would be millimeters. So now this represents the change in the water level from t is equal to 0 to t is equal to 15. I mean 10, sorry. T is equal to 10 to t is equal to 15. So what we can write here is that this value represents the amount of water collected in the can, since it tells us that it's the height of the water in the can, from t is equal to 10 to t is equal to 15 days. Now it says here, at the end of the 60-day period, what is the volume of water that had accumulated in the can? So we have here that this value, or that rather this function, is only from 5 to 60. So that's only from 5 to 60 days. But we were told earlier that during the first 5 days of the 60-day period, so that's from 0 to 5, 3 millimeters of rainfall had been collected. So that means that if we want to find the total amount in the can, well, we want the volume, first of all, but we'll get there. Because what this tells us, this is 3 millimeters, that's the height of water. And then the same thing for when we integrate, that's the height of the water that was collected in the can. So if we want the volume, we're going to need to multiply, right? This is a cylinder, and it does tell us that the radius is 10. I'll get to it. So the height of the can at the end of the 60 days is the 3 millimeters collected in the first 5 days plus the amount after from 5 to 60 of that function, so of s prime of t dt. So that we can get this value from the calculator. So this would be 3 plus, now we're going to integrate. Option 7, my lower limit is 5. My upper limit is 60. And I get 163.5648. 56.48. So if we add 3 to that, we have 166.5648 millimeters. So this is not volume, right? This is the height of the amount of water in the cylindrical can. Now the volume of a cylinder is pi r squared times the height. This is the height, and we were given the radius, as I told you here. Remember that whenever you're doing an FRQ, every piece of information that is given in that FRQ will be used. So if they gave you the radius, that means you must have going to be needing the radius later. So we're going to plug in the radius, so pi times 10 squared times 166.5648. And now I can just put this in the calculator. So pi times 10 squared, which is 100, times 166.5648. And that gives me 52,327.8752. So 52,327.8752. And then our units for volume would be millimeters cubed. And this is the volume of the water that was accumulated. Okay, let's look at another example. The rate at which people enter an auditorium for a concert is modeled by the function r, given by r of t is equal to 1,380 t squared minus 675 t to the third, for t is between 0 and 2 hours, where r of t is measured in people per hour. VIP tickets were sold to 100 people who are already in the auditorium when the doors open at t is equal to 0 for general admission ticket holders to enter. The doors close and the concert begins at t is equal to 2. If all of the VIP ticket holders stayed for the start of the concert, how many people are in the auditorium when the concert begins? So what we're given here is a rate. It doesn't tell us that it's r prime or anything like that, but it does say here that this is the rate at which people enter. So if we're trying to find the amount of people when the concert begins at t is equal to 2, we would have to integrate that rate. So we want to know how many people are in the concert in total. So the total people in the concert is going to equal to the 100 VIP ticket holders that were already inside when t is equal to 0, plus the amount of people that are entering between 0 and 2 hours of RT dt. So again, we can put this into the calculator, but we're going to try doing some of this by hand since this one is not necessarily a calculator question. So we have 100 plus the integral of 0 to 2 of 1,380 t squared minus 675 t to the third dt. So when we integrate, we have 100 plus, this will be 1,380 t to the third over 3 minus 675 t to the fourth divided by 4. And we would evaluate that from 0 to 2. Now, like I said, it's not necessarily a calculator question, but we're going to use the calculator just to get some of these values a little bit easier. So I'm going to actually divide these numbers. So we have 100 plus, let's see here, 1,380 divided by 3 is 460. T to the third minus, now we'll do the same thing here, 675 divided by 4 is 168.75. And again, we're going to evaluate this from 0 to 2. So now we plug in the 2, so 100 plus 460 times 2 to the third, which is 8. Oops, I forgot the t to the fourth here. Minus 168.75 times 2 to the fourth, which is 16. Then if I plug in 0, everything would just be 0 anyway. So it's just basically this value. So we have the 100 plus, now 460 times 8 is 3,680 minus, now I'm going to do 168.75 times 16, which is 2,700. So this will be 100 plus 3,680 is 3,780. So 3,780 minus 2,700, and that gives us a value of 1,080 people. So this means that 1,080 people were in the auditorium when the concert began. Now we're going to switch gears a little bit and look at another aspect that is often asked at FRQs, which is the average value of a function. So just so that you understand how we apply or what is the average value. First of all, how have we found average velocity in the past? Average velocity would be when we take P of A minus P of B and divide it by A minus B, because average velocity would be the slope of the secant line of position. And how we found average acceleration, that is V of A minus V of B over A minus B, since average acceleration is the slope of the secant line of the velocity function. Now the average value of a function is when you multiply 1 over B minus A times the integral of A to B of your function. So let's say if I wanted to find 1 over B minus A times the integral of A to B of A of t. That would give us 1 over B minus A times, now the antiderivative of A of t is V of t, so that would be V of B minus V of A. And if you put this together, what that gives you is V of B minus V of A over B minus A. And if we look above, this represents average acceleration. It is the same exact formula. If we were going to do the same thing here, if we multiply 1 over B minus A times the antiderivative of A to B of V of t, that would be P of A minus P of B. And again, if you put that together, that gives me P of A minus P of B over A minus B. And that's the equivalent to average velocity. So to break this down, what this means is that the average value of a function of f of x on the interval from A to B is defined to be 1 over B minus A times the integral of A to B of that function. So the average value is basically, think of also it's the slope of your secant line, but we can use the integral to find that number. So let's look at some examples. This first one is calculator active, and if we want to find the average value of each of these functions over the interval, we're going to set this up. This is A and this is B. So 1 over B minus A is 1 over 3 minus 1, which is 2, times the integral from 1 to 3 of x to the third times sine x dx. I can put this in my calculator. So I'm going to clear this out. It's x to the third times sine of x. I'm going to adjust my window here to reflect that interval, which is 1 to 3. I'm also just going to, okay, no, that's fine. And let's graph. Now we can integrate. Option 7, my lower limit is 1. My upper limit is 3. And I get 11.6963. So half of 11.6963, which now I'm going to divide that. 11.6963 divided by 2 is equal to 5.8481. And that would be my average value. Now let's try this without the calculator. We have 1 over b minus a, so 6 minus 2, which is 4. And we integrate that from 2 to 6 of the function 2 minus 4x dx. So we're just going to leave this constant there on the outside. The antiderivative of 2 minus 4x is 2x minus 2x squared. Since when we add 1 to the x, we get x squared and then divide by 2. So 4 divided by 2 is 2. And we're going to evaluate this from 2 to 6. So we're going to leave this 1/4 on the outside here. We're going to plug in the 6. 2 times 6 is 12. Minus 6 squared is 36. And 36 times 2 is 72. Minus, now I'm going to plug in the 2. 2 times 2 is 4. Minus 2 squared is 4 times 2 is 8. So we have 1 over 4. 12 minus 72 is negative 60. 4 minus 8 is negative 4. So minus negative 4 would be plus 4. This gives me 1/4 of negative 56. And negative 56 divided by 4 is negative 14. So that would be the average value. Now let's put all of this together. We have here another calculator FRQ. It says a ski resort uses a snow machine to control the snow level on a ski slope. Over a 24-hour period, the volume of snow added to the slope per hour is modeled by the equation S of t is equal to 24 minus t times sine squared of t over 14. The rate at which the snow melts is modeled by the equation m of t is equal to 10 plus 8 cosine of t over 3. Both S of t and m of t have units of cubic yards per hour and is measured in hours for t is between 0 and 24. At time t is equal to 0, the slope holds 50 cubic yards of snow. So for part A, what is the total volume of snow added to the mountain over the first 6-hour period? So we have two functions here. We have S of t, which represents the snow that is added, and then we have m of t, which represents the snow that is melting. So if we want to find the total volume of snow that is just added, that means that we're going to integrate S of t dt, and over the first 6-hour period, that would be from 0 to 6. So I'm going to go to my calculator. I'm going to clear this one out. I'm going to put S of t, which is 24 minus t, or x, times sine. Ooh, this is sine squared, so I got to put a parentheses here. Sine of x divided by 14. I'm closing the parentheses for my angle. I'm closing the parentheses for sine, and I'm squaring it, since sine is squared. Okay, let's go to my window here to make sure it's adjusted. Where the overall interval is from 0 to 24, so I'm just going to graph this from 0 to 24. Now we're not really seeing a lot, which is okay, but I kind of like to see my graph, so I'm just going to go to Zoom Fit so I can get a more wider picture of that graph. All right, so we want to know how much snow was added over the first 6-hour period. So I'm going to go to second calc, and this is the integral. And the reason why I'm integrating, is because we're looking for the amount of snow that was added. And the equations that were given was the rate. So that means that we have to integrate. So from 0 to 6. and we get 142.4131. 4131, and then our units here is cubic yards. So cubic yards. And that's it. For part B, it says to find the value of the integral from 0 to 6 of m of t dt and 1 over 6 of the integral of 0 to 6 m of t dt. And what does each value represent in the problem? So let's start off with the integral of 0 to 6 of m of t dt. So I'm going to go to my calculator. I may need to use this equation again, so I'm just going to deselect it. And now I'm going to type in my m of t equation, which is 10 plus 8 cosine of x divided by 3. All right, so now I'm going to integrate. So second calc, 7 from 0 to 6. And we get 81.8231. And again, this is the amount of snow. So this is cubic yards. Now this represents the total amount of snow melted during the first 6-hour period. Now we're going to find the 1 over 6, the integral of 0 to 6 m of t dt. Now you should recognize this. This is average value because we are dividing 1 over 6. That's b minus a. 6 minus 0 is 6. So this is 1 over 6. The integral of the of m of t from 0 to 6 we already found, which is 81.8231. So we're just going to divide that by 6. So I'm going to go to my calculator once more. We have 81.8231 divided by 6, which is equal to 13.6371. Now our units here is a little different. Yes, we integrated and we got a cubic yards, but this is b minus a, which b minus a is time, right? Because that's the interval represents time. So this is going to be cubic yards per hour. So it's kind of like a rate, and this shows the average amount of snow melted during the first 6 hours. So when you're finding average value, your units is the same units as if it was a derivative, because it's basically the same thing. It represents a rate since we are dividing by time. Now, for part C, write a function a of t representing the total amount of snow on the mountain at any time. Is the volume of snow increasing or decreasing at time t is equal to 4, and justify your answer. Okay, so the total amount of snow, that's the key word here, keywords rather. We want an amount, so that means that we would have to integrate. Now, it tells us at the beginning that the slope at time t is equal to 0, the slope holds 50 cubic yards of snow. So at the very, very beginning, we have 50 cubic yards plus the amount of snow that is added. Now, amount of snow that is added, that would be the integral of s of t. And when you're writing your limits of integration here, it would start at 0 because obviously we can't have negative time, but I don't necessarily know the time, so I'm just going to put t. Like it says at any time, so I want to be able to write a function that would represent for any time. So not just a particular number. So I just put t of s of t dt, because that's the amount of snow that is added. And then the amount of snow that's melting, I would have to subtract from 0 to t of m of t dt. So this is my equation. Now it's asking, is the volume of snow increasing or decreasing? If we're ever trying to find when something is increasing or decreasing, that is the derivative. So that means I'm going to have to find the derivative of this function. So a prime of t is going to equal to, the derivative of 50 is just 0. Now when you find the derivative of an integral, that basically just cancels out because you're finding the derivative of the antiderivative, so that just gives us the function. So this would be s of t minus m of t. So now it's asking me, is it increasing or decreasing at t is equal to 4? So I'm going to plug in 4. A prime of 4 is going to equal to s of 4 minus m of 4. I have both of my functions, so I can get these function values. So again, I go to my y equals here. I'm going to start with s of t, which is my bottom function. My top function. We go to second calc, value, because this is s of t, and I put 4. And I get 23.6822. Minus, now I need m of 4. So I'm going to go back to my y equals menu. I'm going to deselect this function. And now graph my second function. And now we get that function value, which is 11.8819. Which now we subtract. So we have 23.6822 minus 11.8819, which is 11.8632. And this is a derivative, so this is cubic yards per hour. So now we have to justify, or we have to tell whether it's increasing or decreasing. So since a prime of 4 is greater than 0, the volume of the snow is increasing at t is equal to 4 hours. Let's now go to part D. How much snow is on the mountain after 5 hours? Now we want an amount of snow, so that is my A of t, the one that I wrote. So we're looking for A of 5, and that's going to equal to 50 plus the integral from 0 to 5 of s of t dt minus the integral of 0 to 5 m of t dt. So we're going to now plug in those values. I need the integral from 0 to 5, so I got to go to my calculator again. Oops. I'm starting with my s of t. So second calc, my integral from 0 to 5, which is 119.2251. Minus, now I got to graph my other function again. And do the same thing. So 0 to 5, which is 73.8897. So now we just gotta combine all of these numbers. So I'm gonna quit here. We have 50 plus 119.2251 minus 73.8897. And that gives me 95.3354. And this is the amount of snow, so this is cubic yards. Now E. Suppose the snow machine is turned off after 10 hours. Write but do not solve an equation that could be solved to find the time t is equal to k when the snow would all be melted. So in order to write like this, you don't have to actually solve anything. You just need to be able to write down this equation. So if the snow machine is turned off after 10 hours, right? So that means that we would first need the amount of snow that is in or on the mountain at time t is equal to 10. And that is represented by A of t. So we would write first A of 10, because that's the amount of snow after the first 10 hours on the mountain. And then after that, since the snow machine is turned off, no more snow is being added, but snow will be melting. So that would be M of t. But remember, M of t is a rate, and we want the equation that represents when the amount of snow is all melted. So then we would take this value, the amount of snow on the mountain at t is equal to 10, minus the integral from 10 to some value k of M of t dt. Because this would mean that the total snow at t is equal to 10 minus the rate of snow from 10 hours. Minus the integral from 10 to whatever time of the snow melting. So that's what this equation means. And that's it.